I'd like to now have Robert Hernandez to present our next speaker and our keynote speaker. Robert.
Hey, everybody. So next we're going to be having Anita Nikolich. She's a research scientist and director of research innovation at the Information School at the University of Illinois at Urbana-Champaign. She's served as a cybersecurity program director at the National Science Foundation and has spent time in academia, industry, and government. She is the co-organizer of the DEF CON AI Village, a hacker co-op that seeks to make the world and its algorithms a safer place. She is the co-PI of Fabric, a $20 million NSF project that will help computer scientists build the next internet. I'd like to give a warm welcome to Anita Nikolich of UIUC.
Let me see if I can share my screen. Can you guys hear me okay?
Yes, we can.
Okay, great. Somewhat screen share challenge, so make sure I can do this.
Yeah, it's starting.
Okay.
We can see it.
Going to put in present mode and hide my video.
All right, good. Thank you.
Okay. So I'm going to talk a little bit about this test bed we're creating called Fabric, and it's now actually a $23 million effort because we're going global. I don't know if it's hard because you guys are virtual, but does anybody know who this is? If you don't, this is Jay Radcliffe. And in 2011, he hacked his own insulin pump. So I'm a security person by training. I'm a cryptographer and a security person. Jay Radcliffe this is the little radio portion of his insulin pump. He's a diabetic. This leads us to really think about, in the security community, that there aren't a lot of great places to be testing IoT devices at scale outside your lab or within your company. So I think about two things a lot as a security person. One is, how do I break things? And we think a lot lately, particularly about adversarial AI. Secondly, how do I make the internet a better place? So working during COVID from home has led me to really see how awful my internet really is. So what is Fabric? Fabric is, we were funded about a year ago. It's a National Science Foundation $23 million award. If you're an operator, an engineer, or even somebody who's been home for COVID, you've likely stood back in frustration saying, you know, my internet is awful. And mine, certainly at home in Chicago, is awful. I only have a few choices. It's awful for many, many reasons. So our pitch to the National Science Foundation was, we, you know, in an optimistic way, we want to build a better internet. We want scientists to have a place to build, you know, we know protocols are terrible. We know things like DNS and BGP are inefficient. Where can we enable people to test out and build a better internet? So why now? Well, the economics of compute and storage allow for the possibility that the internet is more stateful than we've come to believe. We'll talk a little bit about programming in the internet. So, I mean, people by and large will say, if I had to build a router from scratch today, it would not look anything like the routers we build today. There's all these new capabilities in augmented computing around, you know, a lot cheaper GPUs, FPGAs. How can we reimagine the network architecture so the internet is more stateful? We see a lot more machine learning and AI across the internet. We see the network as a big data instrument where you combine real-time measurements and inferencing in this control loop. So there's no longer, we don't believe, going to be the dumb core, the smart edge, and kind of everything pulled back to the core. With IoT and 5G, we see new high-speed intelligent network edge to the internet. And as people who help the National Science Foundation, we understand that science, particularly with large instruments, and I hear at least one person from Argonne, so I imagine there's others. If you've heard of things like the Large Hadron Collider or Dark Energy Survey, there have got to be better ways to bring back this explosion of science information. It can no longer be, I collect it and I send it over the internet to be processed. So how can we think about doing distributed processing better? And we've seen this continuum of computing capabilities, so it's not just edge and cloud. So what is Fabric? So my task today is to convince you that we are under construction, and my task is to convince you that you should come and try this test bed. So I'm going to tell you what it is. So what is Fabric? We see it as a new paradigm for distributed applications, protocols, and services. So it's now actually international. So it was nationwide, and we'll show the map. We've now expanded to Tokyo, Amsterdam, and the UK. So if you imagine an international programmable network with compute and storage at each node, which allows users to do these computationally intensive programs and protocols to maintain things in the network. We have GPUs, a lot of GPUs, FPGAs, and processors at every node in the network. So we can support quality of service using, we have a combination of dedicated optical 100 gig links. We are lucky because we're building this in concert with the Department of Energy's ESNet, and they are building a brand new network to bring back things like quantum and that kind of science. This, at the very core, it's actually going to be terabit. We're going to interconnect national, international facilities, so everything from high performance computing, cloud like Azure and Google Cloud, wireless, edge nodes, a bunch of different test beds, which you may or may not have heard about, science instruments, and some smart cities test beds, including at least one that's in Bristol, UK. So the goal is to design and test applications, protocols, and services that can run in any node in the network, not just the edge and cloud. So this is our proposed topology. Almost all the blue is, the blue lines and the blue little nodes are co-location facilities where the Department of Energy is going to be. So we're heavily leveraging their build out. And these are by and large commercial colo spaces. So we're going to have very high speed links. So the super core in yellow is at terabit. The rest of the links are at least at 100 gig optical. Some are at higher speeds. Some of this is at layer 1. We're hoping that people can actually do some optical experimentation. And you can see at least 2 places we're going to peer with both a BGP testbed and a bunch of commercial cloud. The little stars, some of you come from government, so the little stars are computing facilities. So our nodes are called Hank nodes. This goes with the theme of fabric. A hank is, I guess, I'm not a knitter, but I think in knitting, a hank is something that a swatch of material or something like that. So our nodes are called a hank. So this is a conceptual overview, and we just literally last week solidified what these nodes are going to look like. But each hank node, we're calling it's essentially a disaggregated router. So you see there's a bunch of storage, mostly kind of near-term scratch type storage, a whole lot of GPU, FPGA, external connections, and the users can get in here. We're collecting tons of information about the testbed itself, and we're collecting information from your experiment. All that is open to you, and if you choose to share your experimentation, maybe the setup, the results, maybe you want to make some labels around it, you can share that with other people. And I can answer questions about this. A little overwhelming, but the slides will be available. So fabric nodes, I'm not going to read all this, but basically that node I just showed you, our goal is to interpose compute and storage that is directly into the path of fast packet flows. So we want, for example, for a large telescope in Chile or the South Pole Telescope or other places where there's large science instruments, for those, we don't want to have scientists just collect the stuff and pull it back to the US. We are hoping that all along the path, they will experiment with combinations of compute and storage and do pre-processing from the point of collection to the point of analysis. So the nodes are these racks. It's essentially one rack of high performance servers, which is Dell. Our friends at Dell partnered with us. And these are all the things that come in the rack. So these are the type of GPUs, the NVIDIA GPUs, some FPGA, and some storage that you as an experimenter can provision. We have some Mellanox connections, and you can choose your favorite speed, whether it's 25 gig up to 200 gig and beyond. A lot of measurement is built in. So at my core, I'm a measurement person, internet measurement, and we wanted to build in measurement. So one of the things we have is really, really accurate packet stamping and timing. So each of these nodes at each location, we have GPS clock source for P2P timing. And you can use that as you see fit. So some people really want to capture very accurate time stamping, and we're able to help you collect it, help you share it, help you analyze it. The main thing is to get set up so that not the facility, but our rack in particular is set up with measurement capabilities for this timing. We have smart PDUs. If sometimes people want to see if they bump up compute or do different things, how does that affect the power? So we have smart PDUs, and we're available because we don't control the optical equipment everywhere, but we're hoping to be able to make optical layer open for measurement. Some people think about things like, if there's a DDoS attack, can I see something at the optical layer? Or I have a new quantum communications device. I want to test it on some strand of fiber where you guys have dark fiber and you have optical on top of it. So all these things are possibilities. Just a very quick overview of the software. There's a lot of different components here. These are the different frameworks. Not to get into too much detail, but just to give folks an impression of the different frameworks that feed into something like a large test bed. So the measurement framework is where you get measurement resources, collect measurement data. Control framework, if you want to, for example, if you want to provision an experiment that tries out your new IoT, and you also want to interface with the real cloud and with a supercomputer test bed, you can do all that through this control framework where you can say, I want my experiment to traverse a bunch of IoT devices in Atlanta, and I want to go to a supercomputing center, and I want to also go through the cloud and experiment with whatever I want to do. You can set all that up, and multiple people can use this at the same time and not see each other's experiments. So this is pretty cool. And then we have this message bus that should something go awry or you want to see what happened to your message, all that data will be available for you, which is pretty interesting. So again, why? The reason for wanting to build a new internet are not just speeds and feeds. That's actually, as many of you know, that's relatively easy. The things we think about are how does experimentation lead us to think about how to enable a private, secure, fair, accessible, more ethical internet. With all the rise in how censorship is done, it's this cat and mouse game about what protocol can I block? How can I get around that protocol? What's my side channel? This cat and mouse game at some point has got to just end. So we want to see what can people do to build a more accessible internet. Part of the way of doing that is expanding the community of stakeholders. So we don't want to just have academics experimenting with building the new internet. We want to expand so that it includes industry and more government partners and others. So we strongly believe that rethinking the internet in terms of no longer just forwarding packets and about how do you allow the network to store and process as they are transported. We feel this is a new paradigm that creates this continuum of options for applications to deploy control and processing in the network instead of the fixed points we're forced to live with today. So we are highly encouraging P4 programmability. We believe that a lot of this hardware is just inexpensive and accessible, that you can buy your own node and help us. And the economics of storage and compute have just changed dramatically in the past few years.